Hey guys, happy Monday. I know, usually meet on Wednesday, but today is our exam 3 review. As you guys pop in, you can drop a hey in the chat box. Why don't you, as a fun way to kind of all be excited today, we can say anything that we did fun over the weekend. And I will say that I went and had lunch on the St. Johns River. So we picked up some to go and we sat, there was a little park, and we sat on the bench and we saw a guy not catch any fish. Hey guys, hi Jenna, hi Christopher, how are you guys today? I'm glad you guys are here. Hi Ashana, I'm glad you're here. Hope you guys had a good weekend. Maybe you got to relax some, see your family, the usual. So today, well, before we get started, if you have any questions about the exam, you can go ahead and drop those in the chat box. If you have questions about anything else, you can also drop that in the chat box. Your mini exam scores have been posted. And if you have any questions, let me know. So we'll give you guys a second for that while people kind of pop in. So I know that today is not our usual day, so we may not have quite as many people around. But otherwise, I'm glad you're here today. Welcome to the Exam 3 review. So while we're seeing if anyone has any questions, otherwise we will start with number 1, which starts in chapter 7. Oh. Okay, so we have 2 questions. So the first one says, I'm struggling with the part of Alex that gives you a 3D model, and then you have to choose which compounds match that model. So in that case, the way I would tackle that question, Jenna, and your other option is after this, you can hop into the Zoom office hours, and we can work some examples to try to give you a little bit more assistance in that case. So what you're going to look for is what I would do is I would draw the structures and then see if they match. Instead of trying to use the structure and back calculate to the compounds, what I would do would be draw all of the Vesper structures for it's hopefully not like many compounds, but 3 or 4 compounds, and then say which of these looks the same as that. So you can try that. Also, feel free to come to Zoom office hours, which will be as soon as this ends, and I'll stick around for at least 30 minutes regardless of when this ends, to answer any questions if you have about Alex objectives or anything else. So I'm happy to help you with that. Anissa asks, so our lowest mini exam grade will be dropped. Yes, and if you go into Canvas, that should already be set up for you. It is definitely 100% set up on my end. So when I go in, I can see that some of your scores have been grayed out. So what you probably will see is that one of them is grayed out. It may say dropped next to it. We'll also see the same thing with your Alex. So for your Alex homework, every week you get up to 10 points for turning in your objectives on time. The lowest of those 2 scores will be dropped. So that has been set up almost all semester. For the mini exams, I set it up and uploaded mini exam 3, what day, Thursday? Whatever day that was last week. So that should already be set up for you. If you were getting alerts about your letter grade, it may have sent you a bunch of things all at the same time. But now that should all be set up for you. If you have questions, pop into my office hours. I can look on my end and make sure that what you see is what I see. Since every now and again, as we know, Canvas basically does something slightly different than I'm asking it to do. So I'm happy to fix that if there's anything right. Any other questions before we get started? Before we get started, I have one other thing I was going to tell you. This exam is significantly less math. It's much more drawing based. It's a little bit more like which of these trends is the right one. So just so that you're aware, it is possible that there will be less drawing questions. Possible is not even, like there's less math, more drawing. So let's look at this. So the first one is a little bit different. Usually we do much more like, what is the answer for this? But in this case, we're asking about the atomic size trend. So atomic size is one of the periodic trends. And so it asks, what is the trend both across a row and down a period? Make sure we're in the right space. So if we look at a periodic table, we are going to decrease as we go across, and it increases as you go down. So the reason it decreases as you go across is due to Z effective. So Z effective or Z star increases as you go across. And so as the effective nuclear charge increases over time, it will basically cause the atom to compact. So it's important to note that atomic size and ionic size are slightly different. And so in this case, it decreases as you go across and it increases as you go down. It is substantially larger as you go down. It decreases to some extent. So it would be really hard to compare two elements such as argon and potassium, because it would not be hard to do that at all. Because argon is substantially smaller than sodium, but what about sodium and krypton? Those two would be a little bit more difficult. So as it decreases as it goes across, it increases as it goes down. So let's think about applying some of our periodic trends. So this asks us to give the correct order for atomic radii of these 5 elements. So we have calcium, potassium, arsenic, germanium, and krypton, which are all in row 4 on the periodic table, which is great because we can basically just rank them from largest to smallest, reading across, or from smallest to largest, reading across the periodic table. So in this case, you could have set these up in one of 2 ways. So the largest in this case is potassium, then calcium, then germanium, arsenic, by krypton. You could have reversed this and basically written it this way. Both of these are equally correct, and I will bring you a little closer so that you can definitely see what I've written on the board. So, what questions do you guys have thus far about atomic radii? And if you have none, you can drop none right in the chat box, and we will move on to number 3, which I will go ahead and put up so that if you don't have any questions and you didn't download the handout, you can start to look at it. But I guess we will leave number 2 up in case you do. Any questions before we start to think about writing the equations for different ionizations? Those are like very close together. Nice, and he said no questions. So I'm not seeing any yet. As always, if you have some, you can drop it in the box. I will also agree that thinking about this part, it's much more straightforward. What is the periodic trend? How do we use that information? So for number 3, we are going to write the equation for the third ionization of aluminum. Now, this is about the ability to remove one electron at a time. So we're removing the third electron. So in this case, aluminum 2 plus goes to aluminum 3 plus 1 E minus. So for any of these, it gives us what is the something ionization. In that case, the third makes the 3 plus ion. And as we know, it's always from 1 electron at a time, removed sequentially. So you make the 1 plus, the 2 plus, the 3 plus, and the 4 plus. If you were to be asked to draw the equation for the electron affinity, that is to make the negative ion, and it follows the same typical trends. What questions do we have? Whoops, wrong one. So we'll go ahead and leave the third question up, which I'm standing in front of, so I'll scoot over. So the next thing we want to think about is number 4. So it asks, which element is the most negative electron affinity? The way you want to think about that is electron affinity can be positive or a very large negative number, which is a quite small number. So we're asking which of these has the strongest electron affinity. Electron affinity, the trend for that is it increases in general as you go across, and then it stays somewhat the same with slight variations as you go up or down. So in this case, we can look at these elements, which are oxygen, potassium, boron, sodium, and sulfur. So in this case, it is the furthest to the right, and it turns out that the electron affinity is stronger for sulfur than it is for oxygen. So for number 4, the answer is sulfur. It's important to remember that when we think about electron affinity, there's 2 ways that you can answer this. In the slides, there is a graphic where you can see the electron affinity for any element. It's important to note that as we go across the P elements, so if we have boron, carbon, nitrogen, oxygen, it turns out that nitrogen has a positive electron affinity, and it's positive because it already has 3 electrons. It has a half-filled shell, so adding another one forces it to become unbalanced, where some of the others don't. So nitrogen and phosphorus don't follow the trend because they are a half-filled shell. So what's next? That, I think, answers all of the questions. So Jane asks, but if you were to put O, would we get some credit? So in this case, no. So for periodic trends, they tend to be an all or nothing type question. Occasionally, some of them will have partial credit depending on what it's asking you to do. But if it asks for you to pick the largest or to put them in an order or any of those things, they tend to just be flat points. You either got it right or you got it wrong. It was definitely that way on the mini exam. On the exam, it will likely be the same. But I haven't finished writing it, so I will. But those are the kind of things you can always come into office hours and ask, and it's possible I will make different decisions. So Any other questions about these type of questions? Because that's really all we have for chapter 7. There are 8 questions today, maybe? I think so. 8 or 9. Let's take a peek. Yeah, there's 8. So this is really the end of the periodic trends. Next, we're going to start to think about all of the different aspects of drawing Lewis-Dot structures, other things. Any other questions? Okay. If you have some, feel free to drop it right in that chat box, and I will answer them as we go along. Christopher, that is correct. So sulfur has more electron affinity than oxygen. It is a slight outside of the trend value, but it is definitely true. And so if you look in the slides, so not in the video, but in the slides on Canvas, those values, there is a table that's out of the textbook that you can look at. Well, that's not going to get any bigger. So next, we're going to start to draw different values. So Muri states, it doesn't make any sense, the oxygen is higher. So in this case, while the trend is that it increases as you go across and typically stays the same, I would always recommend checking the table, particularly for some of them if they're clustered in a region. The table would be advantageous as well. So if you have time, look over the table because it will give you more information. And it will help you identify if there are any that don't follow the rules. So with electron affinity, there are more non-following elements than there are realistically elements that follow the trend. It is more of a general increase, but not necessarily a perpetual increase. And some of that has to do with the size of the atom in comparison to the orbitals and a whole host of other things. Good questions, though. Electron affinity is the hardest of the periodic trends because it follows a rule, but then there are all of these elements, so like nitrogen, phosphorus, arsenic, don't really follow the trend. Same with beryllium, magnesium, and calcium. So the trend gets kind of murky because it's only a general trend, whereas many of the other trends are, in fact, more trends and not just like the idea of a trend. So, So now we're going to start to draw a series of elements or compounds. So we have 6 different compounds where it asks us, draw a Lewis-Dot structure, a Vesper structure, name the electron geometry and the molecular geometry. This is exactly how it would be asked on the exam. For every compound, and it's not on this one, but on the exam, more than likely the central atom would be underlined. And so we'll talk about even this more complicated one where we have CH3NH2. That one would require additional information, whereas the others are not. So let's start with the first one. So we're going to start with SEF6. So the valence electrons are 6 plus 6 times 7. And so we're going to put our selenium in the center and connect our 4 structures as well as the other 2 because we have 6 different fluorines. And we're going to add all of our lone pairs. And so as we add these, it will take an eternity. as you count them up, you'll notice that we have used all of our valence electrons. And so we can also calculate the formal charge. Luckily, we only have one type of bond, so it's relatively simple. So the valence electrons for selenium, or the formal charge, is 6 minus half of 12, which is 0. And for fluorine, it is 7 minus half of 2 minus 6, which is also 0. So this will have no charge. You should always check regardless of what your molecule is. So from here, we need to draw this in 3 dimensions. So that would be our Vesper structure. Vesper structures come in groups, and we can determine what the base geometry or the electron geometry is for this by counting the number of entities, lone pairs or not, lone pairs or bonds, connected to the central atom. So we have 1, 2, 3, 4, 5, 6 different elements or entities connected to the selenium, which means that it is an octahedral structure. So we have selenium. An octahedral looks like this. And so now we have our base structure. We can add our fluorines. All of our fluorines come with their lone pairs. And we show the different wedges and dashes. And so for this structure, both the electron geometry and the molecular geometry are octahedral. So for this structure, there's a couple of things we need to think about. 1, we need to show all of our lone pairs all of the time. The book talks about how in a Vesper structure we don't show lone pairs. So it turns out that what it's really saying is we only show lone pairs sometimes. Therefore, it is my expectation that in these type of questions, you will show all of your lone pairs all of the time. Because it turns out that some of them are important and some of them are not. So what questions do we have about selenium hexafluoride? Do we have any questions about this structure? Okay, I'm not seeing any yet, but as always, if you have some, you can drop it right in that comment box. So next we have GeH4. So our valence electrons are 4 plus 4 times 1, which is 8. Ge in the center, we're going to connect our 4 bonds. We've now used all 8 of our valence electrons. From here, we can then draw our Vesper structure. If we have a steric number of 4, which is the number of things connected to the central atom, we're base tetrahedral. So we're going to put our Ge here in the center. And then we can draw all 4 of our hydrogens in. So in this case, both the electron geometry and the molecular geometry are going to be tetrahedral. So in this case, for this one, a couple of things. We want to make sure that we have the right-ish bond angles in our drawings. I'm not going to use a protractor to ask, but what won't work is to basically look at this and then just draw 90-degree angles. Ooh, so Scott asks a good question. So Scott asks, What determines the dashes and triangles? So wedges and dashes tell you if a bond is coming out of the plane of the board or into the plane of the board. So when we think about this structure, we're going to start with octahedral. So if my body is the plane of the board, we have an element that comes out of the top of me, and then we can either have two elements that come out front or two that go into the back. And so in this case, for octahedral, we have the two that go up and down and two that go this way and two that go this way. And so the wedges and dashes are a way for us as a scientist to give dimensions. Make sure I'm in the camera. We can give dimensions to see that these are in front of the plane of the board, my body, and these are behind. Now, typically, I draw my wedge in front of the dash. There are other scientists who reverse that. Both are mostly correct. If you're also asking for the terms of this structure, does the arrangement of those matter? Not really. So it turns out for this, it spins in 3D space, and so it rotates around. So what I'm going to do is I'm going to put my mask on, grab my keys, not run to my office because then I'll be out of breath, but I'm going to go I have a model kit. So please hang tight, please don't leave. Why don't you, if you have not already drawn structures, you can work on C and D, and I will go get my model kit. Be right back. All right. Sorry about that. Ooh, we have more valid questions. Sorry, I had to run off. Also, don't feel bad about asking questions. I realized when I got here I should have brought the box. So in this case, we have a couple of different entities. Not going to work real well. With this structure, we have two different substituents, and this larger sphere, is our central atom. So when we create an octahedral molecule, we are going to start. These are not like super perfect, but it'll work for today. So in this case, oh wow, this is not the best. Not the best thing I've ever made. But our central atom is here, and the wedges indicate these two that are in front of this plane. And so if you think about it, on this side, we can see that there are two, but if you were to draw a line, the one in the back disappears. So the wedges give you that information. So it's a totally valid question. If we were not digital, we would have brought these to class and then maybe gotten to make some with gumdrops and like toothpicks. But so this is what an octahedral structure looks like. And you can see that we have two that come in this direction and two that are in the back. All right, now I feel like we've gotten way off track. So, are there any other structures, now that we have the model kit, and while drawing more examples is good, I do think that taking time to look at them on the model is better. Are there any of the other structures that you guys wonder what that actually looks like in 3D? Or I can just pull that together. Toothpicks. Y'all bring me great joy. I miss being in person, but this has worked relatively well. So this is tetrahedral. Sorry. So what we see is that no matter how we rotate this, we see three kind of at the bottom and one at the top. And so this is the tetrahedral where these two are in a plane. And then we have one in the front and one behind. And so that's where the wedges and dashes come from. Because I'll speak for myself. I'm not super artistic. Like a wedge and a dash is about as far as I can go. So this is a moderate drawing of what we see. Hey, Scott. So Scott asked, could we see a hexa like the octahedral one? I am not sure what the structure of a hexa is. That might be octahedral, which is the one that we did just a second ago, because hexa means 6. Or are you thinking, so of which are you asking about, a trigonal bipyramidal, a tetrahedral, or a base trigonal planar? So now we will return to your regularly scheduled programming of drawing more structures on the board. But Scott, as you come up with that name, I will surely draw another structure. So for C, we have ASF3, so our valence electrons are 5 plus 3 times 7, which is 26. So we're going to put our arsenic here in the center. We're going to connect our 3 fluorines. We're going to give them all octet. And so now we've used 24 of our 26 valence electrons. And we're going to put the last 2 here on our central atom. So from here we see that this entity has 4 things connected to the central atom, which means that its base tetrahedral. Which looks a lot like the GeH4. And so now we have our 3 fluorines, which we will add on any 3 of these. I like to put mine on the wedges and dashes, but that's a me choice. You can put them anywhere you like. And the last one is going to be our lone pairs. So in this case, our electron geometry is tetrahedral, but our molecular geometry is trigonal pyramid. So in this case, if we have our base tetrahedral structure, when we remove this, we can only see these structures. So the lone pairs are here and they change the bond angles just a little. But what it does is we can only see something that looks like a trigonal pyramid. So in that case, that's what the arsenic trifluoride looks like. So there's a difference between the base tetrahedral that looks like this, or the molecular geometry, which only shows the molecules connected, which looks like this. Ooh, it looks like Scott was looking for the octahedral. I thought so. It's totally okay. So in that case, those are A, B, and C. So now we can look at the next three. So Jane asks, I can put anything on any dashes? In this case, yes. So for all of these, the wedges and the dashes give you the ability to draw. So how did I draw that? Looks like this. So the structure drawn, I don't know, give or take something like this. The bondings are a little awry. So we have two, one in the back, one in the front, side, and the top. Any one of these can be the lone pair because you could rotate. Try not to whack myself in the face. You can rotate these around and change this. So once you decide this is the lone pair, you could draw it with the lone pair back here, and one wedge and two in the plane of the board. You could draw it like this. You could draw it like this with the lone pair coming out in the front. All the wedges and the dashes, there's no specificity about where they are. My only request is that if you put the lone pair at the end of the wedges or the dash, that your lone pair electrons are distinct enough that I can tell that it isn't just like that you drew a dash and then stopped. But I tend to be a pretty good reader, so that usually helps. Does that answer your question? So let's look at D. So D is a little bit of a mixed bag molecule. So in the case of D, we have CH3NH2. So in this case, the carbon is going to be connected to 3 hydrogens and a nitrogen. Now, this one, I would not expect you to be able to answer without additional information. So I'm going to give you the Lewis dot structure right now. Because in this case, for this one, it's kind of outside the scope of what we've learned. This would be more like any of the ones, like the bigger molecules. So let me give you a Lewis dot structure. And this is D. So in this case, if I give you this Lewis dot structure, you should be able to draw a Vesper structure. So this is in the teaching environment, and so I didn't give it to you on the worksheet, but on the exam, if it's something without a central atom, it will either say, this is what the connectivity is in words, or it will give it to you like, using this Lewis dot structure, draw me the Vesper structure. So from here, we're going to start with the carbon, It has 1, 2, 3, 4 things connected to it, so that's tetrahedral. Three of those are hydrogens and 1 is nitrogen. You can put any of them anywhere. I'm going to choose to put my nitrogen here. Now this nitrogen also has 1, 2, 3, 4 things connected, so we've already drawn 1. So now we're going to draw the other 2. And so in this case, now we're going to put our hydrogens and our lone pairs around. I'm going to put a hydrogen here, here, here. I'm going to put my lone pair here on the edge of this wedge, and then our 2 hydrogens. So in this case, we can now look at this and say that for either the carbon or the nitrogen, in this case, we're going to ask about the carbon, the Eg and Mg are both base tetrahedral. So in this case, for D, you would have to have a starting Lewis-Dot structure. We haven't really talked about all of that information. So Mary asks, can I put the lone pairs on top of the nitrogen? Yes. You can rearrange many of these around in different ways. You just need to have a structure that looks mostly like this. Good questions. So on E, if you guys have questions about this one, you can go ahead and drop it in the chat. I'm going to work on E next. Which is IF3. So the valence electrons are 7 plus 3 times 7, so that's 28. Put our iodine in the center, connect to 3 fluorines. Once we've added octet or completed the octet around all of the fluorines, we've used 24 of our 28, so therefore the iodine has 2 lone pairs surrounding it. So then we can count 1, 2, 3, 4, 5 things connected. So in this case, we're going to put our iodine in the center. So now we have our 3 different fluorines. So in this case, we can put our fluorines here. With their lone pairs. We're going to put our 2 lone pairs out here. And so the electron geometry here is trigonal bipyramidal. And the molecular geometry is T-shaped. You would have also, there is another equally valid structure here where the lone pairs are on the top and the bottom and the 3 fluorines are in the center. I will in fact take both in this case. So do we have any questions about IF3 before we look at GaCl3, right? Yes. Any questions thus far? That later. So our last of this section is GaCl3, so gallium trichloride. Now, we want to kind of think about the fact that this also looks like gallium carbon 3 iodines. More than likely, it's chlorine. I'm trying to not use chlorine as often because it can be confusing and it's hard for you to ask. In person, you could have raised your hand and said, is this carbon iodine or chlorine? So if I feel like it is in jeopardy, I may include the name to give you some insight into what that is. Just in case you see GaCl3 and then other information next to that. So the valence electrons here are 3 plus 3 times 7, that gives us 24. Gallium in the center, we're going to connect our 3 chlorines, giving them all octet. So from here, we've used all 24 of our valence electrons. So that tells us that there are no more. And gallium doesn't have to have octet. It can have less than octet, right? So boron, aluminum, gallium, indium, and thallium can all have less than octet. So from here, we can redraw this structure. Not quite in the board. I'll move the camera in just a second. So we're going to have 120 degrees between each chlorine in this case. Whoa. So, whoops, let me move that over. So what questions do we have about any of these structures? I realized on my way walking to class that the Vesper structure key, so there's extra Vesper questions at the bottom in the Vesper module, has not been unlocked, but I will go in and unlock that today as soon as this is over and I get back to my office. So what questions do you guys have about number 5? And if you don't have any, that's fantastic. I personally feel like these values or these types of questions, the more practice you do, the easier it is. Don't forget that there is a document in the Vesper module, I believe, that says the guidelines on how to draw structures. And so that is really important, and I would definitely recommend that you write that down, add that into your notes or something. So if you have no questions on this, you can drop none right in this chat box over here, and we will go ahead and start the next question. Got a lot going on over here. So while this happens, I'm going to move this right up here. I'm going to go ahead and erase the board, and then we'll see what happens next. So in this question, this is a delta H reaction using the bond enthalpy. So in this case, we can start to look at this and ask, what does it look like? Now, for this structure, we're going to make peroxide, which is H2O2. Now, based on this, all of the information we have doesn't actually give us enough information. So we do not have the skill set in order to build that molecule based only on the sequence. So in the problem, I'm giving you the connectivity. So you would need to go in and use to create a Lewis dot structure using the number of valence electrons. So in this case, we want to make sure that we draw our reactants and our products. So our reactants, so we have H2 plus O2 gives us H2O2. So the Lewis dot structure for hydrogen gas is just HH. And so then we have O2, which the structure for that is, it has a double bond. And then for peroxide, we know that it connects H, O, O, H. So there are 14 valence electrons. So the hydrogen has a full octet. Each of these oxygens is only surrounded by 4 electrons. So we're going to add 2 lone pairs. And so then we'll have used 2, 4, 6, 8, 10, 12, 14 of our 14 valence electrons. And because everyone has octet, we don't need to make any double bonds. So now we need to calculate delta H. For bond enthalpy, it's bonds broken minus formed. And so in this case, we're going to break the hydrogen and the oxygen bonds, and we're going to form the OH and the OO bonds. So a number of you on the exam, I could tell were kind of confused on bonds like HH or O double bond O, or really anything, as to how many bonds are being broken. So if we have two elements connected, just like this, if we need to break this bond, there's only one bond that needs to be broken. I'm not going to snap these in half because I might hurt myself. But when you break it, there's only one bond that's being broken, which is different than if you have something connected like this, where there's a bond both over here. Whoops. My goodness. I'm falling apart here, guys. So we have a bond on this side that needs to be broken and a bond on this side. We're going to imagine that there's another atom over here. So that would be the difference when there would be two versus just the one. So in this case, for the hydrogen-hydrogen bond, one bond multiplied by 436. For oxygen, 1 times 495. And when you add those together, we get 931 kilojoules of energy minus what we break. So over here we have two HO bonds and one OO single bond. So this will be 2 times 463 and 1 times 146. Still in the camera. So when you add those up, we get 1072. So broken minus formed gives us a delta H reaction of negative 141 kilojoules. So thinking about bond enthalpy, let me get out of the way. What questions do you guys have either on this example or based on your mini exam 3, which you might have asked about different types of values? And if you have no questions, you can drop none right in that chat box, and we will move on to the next. So this is one example of a mathematical type question that you will see on exam 3 on Wednesday. So Anissa asks, so the equation will be the typo, but corrected. Broken bonds minus the built bonds. Exactly right. So I think about this like Legos. If you have something built together, it takes energy to take it apart and then the energy to build it back together. So this is the only example where it's not products minus reactants. So this one is technically broken, which would be reactants, minus products. So Christopher asks, why do we use the double bond oxygen? So the Lewis dot structure for O2 is double bond O, double bond O. So in this case, if you, for this molecule, you could have gotten that with 12 valence electrons. So we have O connected to O, and if you give, make sure I'm in the camera, yep, one of them full octet, so that uses 8. 10, 12. So here, your options are to either have one with octet and one without, and so then you'll have formal charges, or you can give both octet by creating a double bond. Now, maybe you're like, oh man, what if I had drawn the wrong structure? It turns out that you can earn partial credit, and lots of it, on a question like this. Maybe it asked you to draw something else, and you only had a single bond here. But because you had drawn the reactants and the products, I could see where you made a mistake. So I will give you partial credit for what you got right, and if you understood how to do the calculation, but maybe you used the wrong values in this table. So it's an easy way to get partial credit. Make sure that you draw the structures. It will also tell you to do that in the questions. So, any other questions about bond enthalpy? Those are great questions, and I am so glad you guys asked. Whoops. So our next question says, a molecule contains a PF bond, which is polar, if the bond length is 1.54 angstroms and the F atom has a partial charge of negative 0.245 electrons. What is the dipole moment in terms of Debye? And draw the bond and label the dipole moment. So this is another type of mathematical equation we could do. So in this case, we need to remember that the dipole moment is mu, and mu equals q, which is the charge, times the radius. Now, radius in this case is a slight misnomer because that indicates, or it might suggest, that we need to modify the bond length. It is the charge times the bond length. So in this case, we know that the charge is 0.245 electrons, and the radius is 1.54 angstroms. So we could multiply these two together, and that will give you the dipole moment. However, it asks for it in terms of Debye. So electron angstroms is not the same thing. So we need to add in a series of unit conversions. So we are going to convert angstroms to meter. So 1 angstrom is 1 times 10 to the negative 10 meters. And then we're going to convert electrons to coulombs. So 1 electron is 1.609 times 10 to the negative 19 coulombs. So that's the charge on an electron. Then we're going to multiply that by 1 Debye equals 3.34 times 10 to the negative 30th coulomb meters. And I'm pretty sure I'm off the board. So now we can convert this. This will give us the dipole moment. Now, you might be saying like, oh, I didn't know I have to memorize all of this. You didn't. All of these values are on the equation sheet. So all you really need to do is know how to convert these calculations. So I am going to run this calculation because I forgot. 0.245 times 1.54 divided by 1e10. I don't think that worked. And I get that the dipole moment, so mu, equals 1.82 divide. Because there are 3 significant figures. So once we set this up, we can follow with part B. So part B asks us to draw the dipole moment. And a dipole moment looks just like this. Ooh, so Jenna asks, does it matter that it's negative? Not really. So you could have kept the negative in there. So in this case, it's telling you that it is a negative charge, which also tells you about the dipole moment. So we know that the dipole moment, the arrow points towards the negative electron. So even if you didn't remember that this was a polar bond or the electronegativity, because it tells us right up here in the problem that it's a negative value, we know that the dipole is pulled towards fluorine. So that just gives you a little hint about this so that you could draw this if you were like, you know, I'm not doing the math thing today. So any questions? And that was a really great question, Jenna. So the negative value just tells you whether or not it's the hoarding of electrons or the losing of electrons side of things. Good question. Any other questions? So while you guys think about it, our last question today is about urea. So urea is an essential molecule. You find it in lots of biological systems. Based on the Lewis dot structure that I'm about to put up, we are going to ask for the central atoms to determine the electron domain, the molecular domain, and the hybridization, then count the sigma and pi bonds. But before we do that, Mary asks, how do we do it if there's not a negative value? So if there was, so let me pull that back up. That's super hard to read. Hold on. Put that back up there. So if it didn't tell you, so you can use the electronegativity trend. So fluorine is more electronegative, so in a polar bond, it will hoard the electrons. So in any bond, using the electronegativity scale, you can draw a dipole moment. With the charge on the electron, or the charge on the molecule, the partial charge, and the bond length, you can calculate the dipole moment. So if it didn't have a negative, you would have to remember that fluorine is the most electronegative, and therefore the dipole moment points towards fluorine. Good question. So let's draw the molecule urea. And I will go ahead and erase the board. So in terms of the structure of urea, 1, this will be a bigger molecule. So I will give you the Lewis dot structure. Just like this, where it says, using this molecule, please draw the global structure. So I'm asking you to make a Vesper structure of a large molecule. The bigger the molecule, the more complex it gets. But the idea here is not to look at the whole molecule and then try to figure out what happens. Think about each central atom. So in this structure, we can see H, N, C, and H. They're all in a line. All of those are probably our central atoms. So now we can draw each one at a time. So I'm going to start with the nitrogen on this side. So that is, I think, the left side of the screen. We're going to just start with this one. but it's the same on both sides, so it doesn't really matter. So what I'm going to do is I'm going to count. That nitrogen is connected to 1, 2, 3, 4 things. 2 hydrogens, a carbon, and a lone pair. Which means we're going to start with this structure. Now, you can put any of these anywhere you like. I tend to like my atoms in the plane of the board. It's just my preference. So I'm going to put the carbon here. Then I'm going to put my 2 hydrogens and my lone pair. Now, you could have put any of these anywhere else you want. Once you assign the first one, it matters about the second one. So now we have this carbon. Our central carbon is connected to 1, 2, 3 things. Now that double bond only counts as one thing. A steric number of 3 tells us that it's going to be trigonal planar, which means that our bond angles are 120 degrees. So we're going to get a molecule that looks something like this. Now, again, you could put your oxygen here and your nitrogen here, or your oxygen and your nitrogen. It doesn't matter. I'm going to put my oxygen down here. So now we've connected, we've gotten this far. We have another nitrogen. It also has a steric number of 4. So we're going to put our nitrogen here. We've already got one down. We're going to add the other 2 structures, and so I'm going to add 2 hydrogens and our lone pair. So even if this had another 3 aspects or something else, look at one center at a time and then go from there. So now we have a Vesper structure, and so it asks us about the nitrogen that I'm going to indicate with a star, the carbon that I'm going to indicate with a circle, the nitrogen over here with a square, and then we're going to put a triangle next to this oxygen. So it asks us to name the electron geometry, the molecular geometry, and the hybridization. So we're going to start with our nitrogen over here. The electron geometry, tetrahedral. The molecular geometry is trigonal pyramidal, or trigonal pyramid. And the hybridization is sp3 hybridized. Everything that is tetrahedral is sp3 hybridized, period. There are no changes to that, regardless of whether the electron and the molecular geometry are different. So next, question. So Ashana asks, does the oxygen not count as a central atom? I think it does, but some people wouldn't. I consider a central atom, so I think we will also answer those questions about this one as well. Because you are right, it has a steric number of 3, and so if you would like, we can also add our lone pairs do in fact have geometry, and they are also 120 degrees. It just kind of makes the oxygen look a little crazy. So next we're going to look at oxygen, which has a steric number of 3, which makes the electron geometry and the molecular geometry both trigonal planar. And the steric number of 3 is sp2 hybridized. For the carbon here in the center, the electron geometry and molecular geometry are both trigonal planar. And it is sp2. Now, in perhaps a not shocking twist, the nitrogen that looks exactly like the one on the other side is going to be tetrahedral. and trigonal pyramid. And also SP3. So when we are given these kind of structures, it will ask you to do all of this information. Or you could be given a very complex molecule and ask specific questions about things that are labeled with different shapes in the structure. So what questions do we have about any of the material that's covered on on exam 3? So based on the mini exam, all that we're adding in is the naming of the structures, the bond angles, and the hybridization. So those are really the 3 topics, 3 or 4, that we didn't see on the mini exam. So does anyone have, what questions do you guys have? If you have none, you can drop a none right in that chat box. And I'm going to sign out of here in just a second. Well, if you have any questions. And then I will be in my Zoom office hours. I think it was Jenna earlier who asked a question about an ALEX objective. You can hop into those and I will help you finish up that objective because I don't want you to struggle the night before the exam. Your objectives are due at midnight and the exam is on Wednesday. It will follow the usual time scale. You need to start at roughly 4:30. You will have 75 minutes. You need to upload your work within 10-ish minutes. Please try to make sure that your lone pairs are visible. Sometimes in the pictures of pictures, it gets a little tricky, but it'll take me a little bit longer to grade than usual because there is more drawing, and drawing is just a little harder to grade. If you have no questions, I will see you next week when we talk about Chapter 10. If you have questions, you can ask them here or you can pop into my office hours, and I will be there in just a second. Y'all have a great rest of your Monday. Enjoy the rest of your week. Michael asks, is it 7 sigma and 1 pi? Because I forgot about that. And yes. So there are 7 sigma bonds and 1 pi bond. Thank you for letting me know that. Zach asks, will this be uploaded on the channel and you can rewatch? Yes. You can access that if you go to the channel, and I think it's called Lives. It's another one over, but I will make sure to add it as soon as I walk out of here to the semester playlist. But it'll be there. If you can't find it, send me an email and I will send you a link. Great questions. Any other questions today? I'm not seeing any others, so I am going to go ahead and stop the stream. I will see you guys later, or maybe in my Zoom office hours. Have a great day.